Okay, so let's start. So today we are going to learn mutation testing. And this is today's outline. So we will be learning the overview of what is mutation testing. And then we will learn about mutation operators and how do we conduct mutation testing. And then we will learn how can we combine mutation testing with some other testing techniques. So before we jump into the concept of mutation testing, let's think about a warm-up example here. So in this example, which is the function to find the maximum value of A, B, and C, and assume that we have these four test cases, can we achieve full path coverage for this function here? This is the question. So we have like two branches and we have four test cases. So it should be able to cover all the paths, right? If we craft four test cases correctly, it's enough to cover all the potential paths. So in order to find out whether we can cover the entire, whether we can cover all, whether we can cover all path, let's draw the control flow graph. So this is the control flow graph of this function here. We can clearly see four different paths, right? By combining the two decision points, the two branches. So let's go through the test cases one by one. So for the first test case, A is larger than B, right? So we should take the true branch here. And then C, then temp takes the value of A, and temp becomes 4. And C is larger than 4, so we take the true branch and the second branch again. So we take this. So this is the path covered by the first test case. And let's see the second one. So in the second one, A is still larger than B, right? So we will still take the true branch after the first if. And then temp becomes the value of A, which is 4. And C this time is smaller than 4. So it will take the false branch. So we will take a different path with the second test case. And then for the third test case, A is smaller than B. So we will take the false branch after the first if. So we will take the false branch here, and then the temp value becomes B, which is 3, and 3 is smaller than C, right? So we will take the true branch after the second if. So this is the path covered by the third test case. And then for the first one, A is smaller than B, so we will still take the false branch. And C is smaller than temp, which is the value of B, right? So we will also take the false branch for the second if. So you can see that we can achieve full path coverage with these four test cases. However, can we inject, which is similar to what we did for assignment 2. So can we inject an error that allows the program to pass all the existing test cases, but still produce incorrect results for some other inputs? Can we change just one line of the code to inject such an error? And the answer is also yes. So what we can do is, instead of checking whether A is larger than B, let's try to use a larger than b plus 1. So in this case, if we use the first test case, we will still go through the same path. For the second test case, it's still going through the same path as before. The third one is like still the same. And the last one is also going through the same path as before. So all these four test cases, they will generate the same results for the newly modified program as the previous one. Because the first test case will still cause us to return 5. The second one will still return 4. The third one will still return 4, and the last one will still return 3. So these four test cases are actually not able to capture the bug, although they can achieve 100% of path coverage. And all existing test cases can still pass here because they are still executing the same path as before. So can we come up with a test case to capture the injected bug? The bug we just injected, we just created. So let's try to do a warm-up live poll. So instead of asking you to try out any test case, let's try to limit our selection into these four options. So which test case do you think can be used to capture this injected bug? Which means that capturing the bug means it will cause the program to generate a different results across these two versions of the program. So which test case can capture the bug? So let's see the result. I think you might have done this. Okay, half. So actually, the last one, the last one is the correct answer. So let's see why. So the original program actually returns the largest value among A, B, and C, right? So and let's try to rule out some obviously wrong answer like 1 and 2, because why they are so obvious? Because the second condition here checks whether C is larger than temp, right? And temp is taking the value of either A or B. And we can see that C is always smaller than like A or B, right? So it actually matters. So we don't need to consider the second branch here. We just need to consider the difference of the first one. And the first one here, because we changed the value to be even larger on the right-hand side for B side. So we don't need to care about why the case where A is already smaller than B. So we just need to check whether our test case is sensitive enough to capture this +1 change, right? So let's see why test case 3 cannot find the bug. So for the original program, for test case 3, it will take the true branch after the first if, and then it will take the false branch of the second if, and it will return the value of 4 for the original program. And for the buggy program, it will still take the true branch after the first if, because 4 is still larger than 2 plus 1. And it will still take the false branch, and it will still return 4. So we cannot see the difference of the return values between these two versions of the program. So the test case 3 cannot actually be used for capturing this injected bug. And for test case 4, the execution trace is different. So for the original program, it's taking the first true branch and take the second false branch, and it will return 3. But on the buggy program, because 3 is not larger than 2 plus 1, which is also 3, so it will take the false branch after the first if. And then you can see the difference between the execution traces here, right, on the original program. And C is not larger than temp, so still take the false branch, and it will return the value of 2. So you can see that the return values are different. So test case 4 can be used for finding the bug here. So that's why we can do this. So from this observation, we can see that although we have achieved 100% of path coverage with the original test suite, we may still miss certain bugs. And this is why we need to be aware of the actual values, not just the execution paths, not just covering all the possible execution paths. We also need to be aware of how are we covering those paths, which values did we use when we are reaching certain location of the program. So we need to be aware of data flow. This is just a reminder of what we have learned. And we can also see that boundary value is like indeed helpful here, right? Because like the boundary 3 is like more at the boundary of B plus 1 here. So so-called boundary is helping here. And another thing that we need to think about is the original test suite is already good enough because it can achieve 100% of path coverage. But it is still not perfect because it still can miss some bugs. And if we put test case 4 into our test suite, we can build a better test suite, right? So how can we evaluate the quality of a collection of tests, which is also known as a test suite? So how can we evaluate the 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 quality of this test suite? So let's think about this problem. So so for target programs or target software, we create test cases to evaluate their quality. And we need something to evaluate the quality of the test cases, right? And then do we need something else to evaluate this thing here? And this will give us an endless recursion. So we have to have some solution here, right, to stop this endless recursion. And you see that this is not part of the hair of this person. This is actually a shoulder of like a larger person in behind. So it's like endless recursion here if we do this. So what we need is we need to end this recursion. We need to have some solution to really evaluate the quality of the test cases. So we have test cases and we have target programs. So what we did was we use test cases to evaluate the target programs. So if we think out of the box, can we create some target programs to evaluate the test cases? So like what we did for the example just now, can we inject some tricky bugs that couldn't be captured by the test suite to evaluate, or that are hard to be captured by the test suites to evaluate the quality of the test cases. So this is what we can do. So we can use test cases to evaluate target programs. So we can also use different target programs to test our test cases. So we can avoid the recursion here. And the approach of creating new target programs for testing test cases is known as mutation testing. So the idea is we modify the original target program to create mutants to evaluate, to test the test cases. So you can see the keyword here is called mutant. And if we talk about mutant, it is actually a word borrowed from biology, which refers to like adding some small variations to some organisms. So if you think about mutants, you may think about this, and this is actually from the Resident Evil game. And if a test case can capture the bug or the modification applied to the mutant, then this test case is said to be able to kill that mutant. So you can see the keyword kill here. So any test case that can kill the mutants is considered as a good test case, right? So if you kill the mutants, then it's good. So this is a in-game character that can kill the mutants. So if a test case can kill the mutants we create by modifying the original program, then it is a good test case. So in this way, we can use the ability of killing agents to killing mutants to evaluate the quality of test cases. And that is like an informal description of mutation testing. And now let's try to come to some formal definitions. So a mutant P is like a result of applying some small changes to the source code of the original program. So this is a mutant. And given an original program P, a mutant P prime, and a set of test cases such that every test case inside the test suite can pass the original program, which means that the test cases must not fail on the original program. Otherwise, there are some bugs in the original program, right? So the test case, so it means that the original program must be free from bugs that could be captured by the test suite. And then if at least one of the test case fails on the mutant, on the new program, then this new program is considered to be killed by the test suite or by that particular test case. So this is the definition of killing. And then for any mutant that is able to pass on all the test cases we have, then that mutant is considered as a live mutant, which means that it survives the killing from the test cases. And suppose we have an original program P, and we have a set M of the different mutants of P. And then we have and then for the test suite T, X mutants were killed out of the Y total mutants, then the ratio of X divided by Y is the mutation score. So the mutation score is basically the killed mutants divided by the number of total mutants. So do you think the mutation score is the higher the better or the lower the better for describing a test suite? Do you think it's the higher the better or the lower the better? Like, remember, if a test case can kill a mutant, then that test case is considered to be a good test case, right? And the number here is calculated by the number of killed agents divided by the number of total agents. So this mutation score is the higher, the better, right? So if a test suite has a higher mutation score, then it means that it has a higher quality. So if you know the lore of the game of Resident Evil, so how does the umbrella company create mutants? Like these mutants, how are they created? So they were created by some virus, using some virus to apply to some humans or some other creatures to create these mutants, to trigger the mutation. So, but how do we create mutants for programs? We know that, okay, we can create mutants with some virus, but how do we create mutants for a program? So we try to apply mutation operators. So mutation operators are like the viruses here that can trigger the program to turn into other forms. And now let's learn about the different types of mutation operators. So there are some key characteristics for these mutation operators. So these mutation operators are intended to model the most common types of faults. That is to make sure that we are injecting some faults that are likely to happen in real world during development. So this is the first characteristic. The second one is they are designed to be applied for any code without human intervention, which means that we can use them to automatically create mutants, right? So we don't need to manually inject these errors. And the third characteristic is actually determined by the first two, because we want to inject some common types of faults. We want them to be easy to be applied. So most of the time they are just most simple syntactic faults, like replacing one variable reference with another, like changing a comparison from smaller than to smaller than or equals to. So these are likely some typos or some, like minor implementation faults, referencing a parent class instead of a child class. So we're referencing the wrong class. So these are the characteristics of different mutation operators. And then we have several different levels of mutation operators. So the most basic level of mutation operators are the modifications which are applied to the operands of the program. So one of the biggest group of operation modification is X for Y replacement. For example, we can replace one constant value with another constant value. We can replace a constant with a scalar variable. Scalar variable means it's not a vector, right? It's not an array or list. So it's just a single value variable. And then we can also do something reverse. we can replace a scala with another one, and we can do all these. We can do all the operand level of mutations. You don't have to remember all these. These are just some examples of typical mutation operators that we can use. And an example is here. So for example, if the original program is like this, like 2 lines of Python code, what we can do is we can replace this 18 here with another constant value here, right? Of course, we can also try to replace this 18 with some other variables, not just constant values. So this is x for y replacement. And we can also try to do some expression level of modifications. So operators and operands are, if we combine them together, we can build some expressions, right? So for arithmetic operators, like these binary operators, like unary operators, or some shortcut operators. For these operators, what we can do is we can do some replacement, right? We can replace one operator with another. So we can replace them. This is like if we, for example, if we replace a unary operator with this one here, it's to simulate the case where a developer made a typo. So maybe the developer accidentally typed one more plus, then it becomes this one here, right? So the fault is like simulating some typos made by the developers. And of course, we can also try to do some insertion of arithmetic operators, like inserting some additional operators inside the expressions. And of course, with insertion, we can also have deletion, right? We can delete some mutation operators from the expressions. And for the example program, what we can do is instead of using a times here for this value, we can replace it with plus. Of course, we can also try out other binary operators here. So this is just to simulate the cases where the developer made a typo or just wrongly designed this formula here. So this is arithmetic related modifications. And of course, we can also have some conditional operators like these binary operators like AND, or, like bitwise AND, bitwise OR, bitwise XOR. We can also have unary operators like this is negation and this is bitwise negation. And of course, we have relational operators which are used for comparing the two values. And we have shift operators as well. And what we can do is for these operators, we can also do the similar things. We can replace, we can insert, we can also delete. Inside this example here, what we can do is quite similar to what we just did for the example program. So instead of using larger than or equals to for the age comparison here, we can replace the operator with a simple larger than. So this is an example of modifying the expressions. And of course, we can also have some shortcut operators, like how these are used for both modifying the value and assigning some values, right? And we can also do this replacement, insertion, or deletion. And we can also try to do absolute value insertion. So we can replace a sub-expression with the absolute value of that sub-expression here. So this is to consider the arithmetic errors which we can make by mistaking the values of the value range of some parameters. And we can also try to use constant to replace some predicates for some conditions like that need to be calculated from variables. We can replace them with some constant values like constant true or constant false. And if we move one level up, we can also try to do statement level of modifications. Similar to what we can do for these operators, what we can do for statements are we can try to delete some statements. We can replace some interesting statements like the statements in the switch cases, or for the end block of a compound statement like if, like for loops or while loops, we can move the closing bracket to include some statements to the coding block, or we can remove some statements outside the code block, right? By moving the closing bracket here. And for Python, we just move the indentation of the statements. And an example here is what we can do is we can try to delete this single statement here from this if branch. And if we do so, normally we will also need to add a pass here if that is the only statement inside the if, because we don't want the program to crash. We still want the program to be able to run, but just do our purpose of removing that statement. So we don't want the program to crash earlier, like before we don't want the mutant to be like not executable, right? And apart from statement level of mutation operators, we have a big family of applying mutations according to object-oriented properties. So we have this encapsulation or inheritance related modifications. I will do a speed run of this. So you just need to use these slides as a note for creating different mutation operators. And we have like modifications that could be applied according to the inheritance relations, like how these overriding like or inserting some the keywords related to the inheritance relation, like the super. And we can also try to apply some renaming or deletion of some key functions. And of course, another important characteristic of object-oriented programming is polymorphism. So we can also do modifications in accordance to polymorphism. So what we can do is we can create new method with the child class rather than a parent class. For instance, we can also try to declare variable class with like parent class. So we can switch between the usage of child and parents. So polymorphism, and of course we can try to do some castings. We can also try to do some like reference modifications. So these are all the modifications we can do. So these like how of course we can also try to do some overloading to test polymorphism. And you don't need to remember all these like mutations. You just need to remember some basic ones, like applied for operator or operand level or expression level or statement level. But for object-oriented level, they are just too tedious to be learned here. And now let's continue to how could we conduct mutation testing. So a typical workflow is like this. So we need to select the mutation operators. Just now you can see that we have all these big families of different mutation operators. So we need to select suitable mutation operators that could be applied to our target program. And then we can apply these mutation operators one by one to the target program to create mutants. For example, we can delete the statements one by one from the target program to create different mutants. And then we execute the same set of test cases on both the original program and the mutants. So if the tests can pass the original program but fail on the mutant, then this mutant is killed. And if a mutant is not killed by any test case, which means that it can pass on all the test cases we have, then this mutant is considered as alive or it has survived this. So let's try an example to practice the process of doing mutation testing. So let's consider this program here. So this program calculates the shipping fee, which accepts two parameters, the total number of shipping and the whether and the membership check. So if the total number is larger than 100, larger than or equal to 100, then we will always remove the shipping fee, no matter whether the person is a member or not. And if the total number is smaller than 100, and if the person is a member, then we will charge the person $5. Otherwise, we will charge the person $10. So we check the total number first, and then check the membership with this function here. And let's assume that our initial test suite, we have 3 test cases inside. So the first one is we have a total number of larger than 100. And we don't care, actually, we don't need to care about whether the person is a member or not, right? It should return as 0. And the second one is if the number is smaller than 100, then we need to check whether the person is a member or not. If the person is a member, it should return 5. If the person is not a member, it should return 10. So we can see that these 3 test cases are actually enough to cover all the possible return values of this function here, right? They are actually created to trigger all the 3 different returns. And now let's check for the mutants we can create. So the first mutant, we create this mutant by changing the larger than or equal to 100 with larger than. So this is the first mutant we have. The second one is we change the return 5 to return 10. And the third one is we just do a negation of the second if condition here. So instead of checking if it is a member, we check if the person is not a member. So this is somehow a very likely to happen type of bug. And for the last one, instead of returning 10, let's try to return 0. So this is also a constant replacing mutant. So let's see if the initial test cases are enough to kill all the test cases, to kill all the mutants. So for the first one, we change from total larger than or equal to 100 to total larger than 100. So what will the first test case return? So 120 is still larger than 100, right? The behavior of the program is not affected. So it will still return 0 here. And for both of the other 2 test cases, because 50 is still smaller than 100, then both of them will keep their original behavior. And for the second test case, the mutant will still return 5. For the third test case, the mutant will still return 10. So the mutant is not killed by any of the test cases here because all the test cases will give us the same return values on both the original program and mutant M1. And for the second mutant, can we kill it with one of our test cases? And if yes, which test case do you think can kill this second mutant? The second mutant is actually very quite obvious because all the three test cases are designed to trigger the three different returns, right? So the second for the second mutant, we are returning 10 instead of returning 5. So for the original program, the second test case is going to trigger this return 5 behavior, right? So, and we replaced this statement with return 10. So on the mutant, the second test case will return 10 instead of 5. And the return values are different on the original program and the new target program. So the second test case will fail. So it could be killed. What about the third one? Can we kill this? Can we kill this mutant with any of the test cases here? And if the answer is yes, which test cases could be used for killing this mutant? Actually, both the second test case and the third test case can be used for killing this mutant, right? Because we just change the number from if we just change the statement from if not member to if not member. So if we do this 52 here, and if it is because we change it to if not member, it will return as 10. And this will fill the test case. We fill the assertion here. And it's the same for the third test case here. It will return 5 rather than 10. So both of them can kill this mutant. So this mutant is also killed. What about the last one? So can we kill this M4 mutant? If yes, which test case could be used for killing this? Actually, the third test case could be used here, right? Because the third option, the third test case is used for triggering the return 10 of the original program. So we can use it to capture the change for that line of code. And in the mutant, because we are changing the return 10 to return 0, it will return 0, and 0 is not equal to 10. So it will be captured by the third test case, and it will be killed by that test case as well. So this is like the survival tracking for all the mutants we can have. And then the question is, what is the mutation score here? Do you still remember the definition of mutation score? Like, it's the number of killed mutants divided by the number of total mutants, right? So the mutation score of the three test cases we can have here is actually 3 divided by 4, just 0.745. And do you think we can create a test case that can kill M1 as well to enhance the test suite? We can actually create one, right? According to the change. So what we can create is we just make the value here exactly 100. We just make it exactly 100. So, so you can see that this test case is better than using this one here, right? Because this one can improve the mutation score, can increase the overall quality of our test suite. And actually the design of this test case is reflecting kind of echoing our design guidelines for using boundary values to do testing, right? So this is why boundary value testing is important. And that's all about how can we apply mutation testing in practice. And we also need to think about in which situation can we just use mutation testing? Because mutation testing is not applicable at any stage of development. We need to think about when or for what kind of program could we use mutation testing to evaluate the quality of the test cases we create. Remember the characteristics of the mutation operators. Most of them are actually small syntactic mistakes here. And programmers, they are created because programmers to simulate the real errors made by the programmers, right? So programmers do make such mistakes. However, in practice, most of the faults created, or many of the faults created by the programmers are actually conceptual or logical errors. These conceptual or logical errors could not be reflected by these um, these small syntactic errors, right? Because, for example, these conceptual errors are often are often made because of the wrong assumptions about some requirements or wrong interpretations of the requirements, right? So these are some high-level faults. Or maybe the programmers just forgot some like restrictions from the requirements. So in these cases, we need to think about, is mutation testing still viable or applicable in such cases, right? Where programmers could make logical errors. So we know that if the mutants cannot capture real mistakes made by the programmers, then these mutants are not so good to reflect the real quality of the test suite, the capability of finding real bugs of the test suite, right? So we wanted to simulate, to represent real faults. However, some faults are high level, like we have discussed. So we need to have the assumption that the target program for us to create mutants is already like kind of well written. So we need to assume that the target program we use for creating these mutants are free from high level bugs or logical bugs. Then we can apply mutation operators to create some errors, which can simulate like simple errors like typos or some like simple misthoughts of the design. So if like in the early stage of development, where the developers may not be so sure about the requirements, and maybe they are still missing some requirements or waiting for some other requirements to come in, then it's not very meaningful to do mutation testing on those programs. And another thing we need to consider for mutation testing is that we need to assume that there are coupling effects inside the program. So coupling effects means that because many faults created by mutation testing are small errors, And conceptual faults, like those high-level faults, are made up of accumulation of smaller faults. And and these complex faults may like require larger differences, like in the text of the code. So in some cases, if the complex error is could be made up of simple changes of the program, then mutation testing could still be applied. For example, for the test case, for the example we created, for the warm-up example, we switch the right-hand side from B to B plus one, right? So sometimes when developers are thinking about some loop boundaries or stopping criteria for loops, they may make errors or mistakes when thinking about these errors. Those are actually high-level conceptual errors, but they can still be reflected as simple syntactical changes. So in that cases, we call them coupling effect. So large or complex errors are coupled with a mixture of smaller errors. And if this if this coupling effect assumption is hold, then we can still think that mutation testing could be applied for that program. So this is basically the coupling effect. So if both the competent programmer hypothesis and coupling effect hypothesis hold, then we can consider mutation testing is effective on this type of target. So it's like either the the program is free from high-level bugs, or the program and the program, like some of the errors in the even there are some high-level bugs. Even if there are some high-level bugs, the high-level bugs could be represented by some smaller ones, an accumulation of some smaller ones. Then we can still apply mutation testing. So that's the explanation of this hypothesis. And before we continue to discuss the quality of the mutants, let's pause here and have a rest of 10 minutes. And I'll see you at 7 past 4. Okay, so let's continue. So just now we mentioned that we don't need to recursively test the evaluator of of the the evaluator of the test cases, right? Just mutating the by just using different versions of the test target program to test the test cases. But we still need to somehow think about the quality of different mutants because we can generate so many mutants, right? We can have like so many mutation operators which can be applied to different levels or different components of the program. So once we have these many mutants, how can we evaluate their quality? So in order for a mutant to be valuable to be used for testing, these mutants must be valid, which means that the mutant should be able to compile and execute, right? Because we for testing we need to feed the test input into the target program and execute the input and generate the output. If the mutant is mutated so wrong that it couldn't even compile or execute, then not it's not usable for testing. So mutants must be valid. So that's the first requirement. And they should better also be useful, which means that they are like more likely to expose the design errors of the they're more likely to capture the design errors of the test suites. So it should provide some information of how the system works, right? So can a mutant be valid but not useful in this case? So which means that is every valid mutant also considered as useful? Actually, the answer is no, right? Because some mutants remain live. So a live mutant actually is a useful mutant that exposes some errors, right? But some mutants can remain alive just because they are equivalent to the original program. For example, if we change from like from maybe A is like larger than 10 to A is larger than 5 plus 5, then it's the same. So it doesn't trigger new behavior. So if they are equivalent to the original program, then this mutant is considered as not useful. And sometimes the test suite is simply not useful or not couldn't be applied for that mutation. Why? Because sometimes we may create some conditions that because we can modify the expressions of the program, right? So sometimes be uh, we cannot be used. We cannot create the condition so correct that it can be captured by the test suite. This is an example here. So for example, if we just create A is if the original program is A equals to B, and we create these two agents, these two mutants, then these two mutants cannot be differentiated if we just use A equals to B in the test case. So sometimes it's not very like adequate to be applied just because of the different combinations and natural complexity of these conditions. So now let's come back to the mutation score and coverage of mutant. So remember, we just learned the mutation score is like the value of the ratio of killed mutants divided by the total number of mutants. And this can be used for measuring the quality of the test suite. If a test suite has a higher mutation score, then it is considered to have better quality. And for mutation coverage, it is considered to be able to subsume some of the structural coverage metrics. And the concept of subsumption is discussed in lecture 5, which means that if we can achieve certain level of mutation coverage, then we don't need to care about structural coverage at all. So this is the case. And let's see why. Because for statement coverage, what we can do is we can simply delete any statement from the program and try to execute the program and see. And in this case, we are actually kind of making sure that the test case can cover all the statements, right? Because if we delete a statement and the test case can still run on that program, then this test case may not be, the test suite are not covering that statement at all, right? So mutation coverage can subsume statement coverage. And it can also subsume branch coverage. What we can simply do is we can simply use some constant true or false values to replace all the branches, the branching conditions. For example, we can use a combination of all true, all false, or true false, like all the permutations of different values here to replace those conditions with just constant values. And in this case, if all the test cases can still pass, then it means that there are some branches which are not covered, right? So this is why mutation coverage can be used to subsume some structural coverage, because we can apply different mutation operators on different levels exhaustively. So that's why. And there are some practical considerations when we try to apply mutation testing. As we can imagine, mutation testing could be very expensive because we must run all the tests on all the mutants in order to kill the mutants, right? And this is like, and what's worse is that typically we may create too many mutants because we can like literally change anything of the program, of the original program. So we could just create so many mutants and we need to apply all the tests on each of the mutant. So this is a very large effort. So if we have limited budget, so which means that cost is a main consideration here, we can actually use weak mutation testing. And the key idea of weak mutation testing is to reduce the number of mutants by applying multiple mutation operators to the mutant. And this is a typical workflow of weak mutation testing. So what we do first is we just put multiple thoughts into a single mutant. And you can see you can foresee actually the potential issue here. If we put multiple faults into this single mutant, what if it is not killed? It stays alive. Then there are multiple faults that are not captured, right? We need to locate the exact location of fault, right? So what we need to do is we need to divide the program into segments and track the internal states of both the original program and all the mutants when executing that segment. And we kill the detected mutants when the intermediate values doesn't match, rather than waiting for the whole output. And this can also help us to decrease the number of test executions. So let's try to use the warming up example here to show you how should we do, what's the difference between normal mutation testing and weak mutation testing. So let's assume that this is the original program, and this is the mutant we created by adding a 1 to the right-hand side operand. So what we do here is we can have this normal. Let's also assume that we have the test case here as the test suite. And for the normal mutation testing, we just execute the original program, get the return value here, and then we execute the mutant and get the value here. And we compare the difference between the two outputs, we can find the bug. And for weak mutation testing, what we do is for the original program, we run this test case. And this test case is the execution path is still the same as you can see. But instead of tracking the output value, we keep track of all the intermediate values at each step. For example, after executing this temp equals to A here, we keep track of the value of A, B, C, and temp. It's the same for all the other statements. So we keep track of all the intermediate values, all the values of all the variables at certain location. And when we execute the mutant with the same input, what we do is at each step, we just compare the intermediate states. We just compare the intermediate values here. So here at the first step, when we execute the mutant, temp is not assigned with any value, and the value of A, B, and C are all the same here, right? But once we reach this line of code, temp equals to B, we know that temp is assigned with a value of 2 here. But on the original program, when we reach this state, temp is taking the value of 3. Then we can know that, okay, there are some misalignments between the two executions, between the intermediate values of the two executions. So we can stop here and declare that we found the bug. So this can help us to reduce the number of executions. So this is weak mutation testing. And then we have mutation testing versus mutation-based fuzzing or mutation-based testing. So fuzzing is like a concept, a useful technique, a practically useful technique we will be learning in the next week. So the basic idea of fuzzing is to randomly generate a large amount of test inputs and run them with the target program to see if there are any bugs or crashes triggered. And fuzzing can be mutation-based or generation-based. So that's why you often hear the term called mutation-based testing. However, mutation-based testing is very different from mutation testing because They are actually totally different, although they sound similar. So mutation-based testing is to apply some variations or some small modifications or changes to the test cases to randomly create test inputs. So the mutation-based testing here, the mutations are applied to the test cases or test inputs. But for mutation testing, the mutation is applied to the target programs. So it's totally different. So this means that we can actually use mutation testing to evaluate mutation-based testing or mutation-based fuzzing. So because mutation testing is to create target programs that can test the test cases, is like a test for test. So this is the relationship between mutation testing and mutation-based testing or mutation-based fuzzing. And there is actually a research paper which discusses about using the mutation testing for mutation analysis for evaluating different fuzzing techniques or different mutation-based testing techniques. And if you are interested into the source code of this paper, it is here. And we actually consider to do some practice for assignment 2 or 3, but it's very hard to use. But what we care about this paper is like inside the paper, you can see the design mutation operators from them. It's actually very similar to what we discussed in the previous slides. You can see that they are also trying to replace the relationship operators, right? The relational operators. They are also trying to like do some like arithmetic operators, right? Like switching the shift kind of thing. And all these mutation operators they have applied are actually used to simulate the real errors that could be made by the developers. You can see all the different mutation operators they designed. So you can see they also try to mutate equals to equals to just one single equal. So this is like some kind of typo developers could make, or some like new developers may make these type of errors. So we can actually, you don't need to remember all of them, of course. This is just a reference to give you a feeling that, okay, this is how we can design these mutation operators. And it's actually very similar to what we have documented in our slides. So the design of these mutation operators are actually to reflect real errors that could be made by the developers. So they are not just like randomly designed, or they are not designed out of nowhere, but they are like designed with some considerations to simulate real faults. So that's all for today's lecture. And before we end, let's have a quick recall of what we have covered today. So as I go through this, you can try to see if you can still remember the key concepts. So for mutation testing, the purpose is starts from a question like how can we evaluate the quality? So we use test cases to evaluate the quality of programs or software. But how can we evaluate the quality of our test cases, right? So the intuition is very straightforward. We can use test cases to evaluate programs. So in return, we can also use programs to evaluate test cases. Then the key becomes how do we create these programs that can be used here, right? So that is mutation testing. So what we do is we try to create mutants. And a mutant is a program that is similar to the original program, except for some small modifications. And those small modifications are known as mutation operators. And a mutant is considered to be killed, so the keyword is killed, if at least one of the test cases in the test suite cannot pass on that mutant, then that mutant is killed. And a test case that can kill a mutant is considered to be a good test case. And the mutation, the definition of mutation score is the number of killed mutants by this test suite divided by the number of total mutants. So the mutation score is the higher, the better for a test suite. So this is the definitions and basic concepts of mutation testing. And for mutation testing, the key thing we need to consider is the mutation operators. So the mutation operators are often like very small syntax errors that could be made. And the reason of using these small syntax errors is that we would like to automate the creation of mutants. So we can massively create the mutants. And there are different levels of creating mutation operators. We can create operand levels of mutation operators. We can create expression level of mutation operators. We can create a statement level of mutation operators. And we can also create some mutations according to the object-oriented design principles. So we can create mutation operators at different levels. And as for conducting mutation testing, what we do is we try to select a number of mutation operators that are suitable for our target program first. And then we apply these mutation operators to create mutants. And normally, one mutation operator applied returns one mutant. And once we have the mutants, we can try to run all the tests against all the mutants and the original program. If the test can pass, if a test can pass the original program, but fail the mutant, then this mutant is killed. And if a mutant is not killed by any test suite, by not any test case, then this mutant is considered as alive. And we can use the number of killed mutants to calculate the mutation score, of course. So that is mutation, the practical approach for applying mutation testing. And mutation testing may not be always applicable to programs because some programs are simply too buggy. They have some very high level bugs. So we need to have the assumption that the developers are already building a software that is nearly complete, that is almost correct. Then we can apply mutation operators to create mutants based on that program. And the other assumption is we need to assume that some very complex or real world errors could be made up of accumulation of small syntax errors. And that is the second assumption for the mutation testing to be practically applicable. So these are the two hypotheses. And we also need to think about the quality of mutants. So for the quality of mutants, a mutant should ideally be both valid and useful. So valid means that the mutant must be able to compile and execute. Otherwise, that mutant is not even usable for testing, right, if it cannot run. And a mutant should also be try to be useful because some mutants cannot be used to differentiate different test cases. So in some cases, so those mutants are considered as not useful. And lastly, this is for some concepts clarification. So you may sometimes encounter like mutation-based finding or mutation-based testing. And actually, mutation testing is totally different from mutation-based testing. Mutation-based testing is just to use some mutations or modifications to create test inputs randomly. But mutation testing is to evaluate the quality of test cases, which is like for a different, totally different purpose. So that's all for today's lecture, and thank you for coming. Thank you.